There is one handout being passed around, it's chapters 4 and 5. So be sure to pick it up. And just a reminder that there is a homework due next Wednesday. So we have homeworks due every week in this course as well. So in last class we covered chapters 1 to 3 quite quickly rather, because it was mostly a review of 6450. And one of the key ideas we covered last class was the connection between continuous time and discrete time systems. So we have continuous time, discrete time. The specific example that we saw was that of an orthonormal PAM system. The architecture for a PAM system is as follows. You have xk, a sequence of symbols coming in. They get into a PAM modulator. What you get out is a waveform, x of t, is what the PAM modulator produces. You have additive noise on the channel. And what you receive out is y of t. So y of t is the waveform that the receiver receives. And at what a canonical receiver structure is to do a match filter followed by sampling. So what you get out is a sequence of symbols y of k. So this is a structure for an orthonormal PAM modulator. And the continuous time version of the channel is that you have y of t, which is received at the receiver. It's x of t plus n of t. The discrete time model is you have the symbol y of k at the output of the sampler. It equals x of k plus n of k. Now, basically, we say that the two systems are equivalent in the following sense. If you want to make a detection of x of k here at the receiver, y of k is a sufficient statistic given that y of t is received at the front end of the receiver. So that's the equivalence between discrete time and continuous time. And the way we established this fact was by using this theorem of irrelevance. The noise here is white Gaussian noise. So if we project it onto orthonormal waveforms, the corresponding noise samples will be IID. The noise will be independent of everything which is out of band. And so there is no correlation among the noise samples, and y of k is a sufficient statistic to detect x of k. So that is the basic idea. Now, the similar architecture also holds when your continuous time system operates in pass band rather than base band. Except the main difference now is instead of a PAM modulation, you have a QAM modulator, and your symbols x of k and n of k will be complex numbers rather than real numbers. Now, the connection between continuous time and discrete time systems can be made more precise by relating some parameters in continuous time with those in discrete time. Okay, so we have continuous time parameters and discrete time parameters. So a continuous time parameter is a bandwidth. W. The discrete time parameter is given by symbol interval. T, and the relation is T equals 1 over 2W. This is for a PAM system. Okay? So something is shown in 6450, and it's shown by using Nyquist's ISI criteria. Do not want to have ISI in the system, the maximum symbol rate, or rather the minimum symbol rate will be 1 over 2W. You cannot send symbols faster than this rate. The second criteria is power, which is P here in continuous time. In discrete time, the equivalent parameter is energy per 2 dimensions. It's denoted by ES, and ES is related to P by using ES equals 2PT. Note that this is per 2 dimensions, meaning it is in PAM we have 1 symbol per dimension, so this is per 2 symbols. This is energy per 2 symbols for a PAM modulator, and the relation is ES equals 2PT. T is the time for 1 symbol. We are looking at energy per 2 symbols, so we multiply P by 2T. Okay. Noise in continuous time is AWGN. So it's an additive height Gaussian noise process. And the power spectral density is flat on positive support of bandwidth, and the height is N0. Okay, so this is how the spectral density is. In 6450, we looked at double-sided power spectral density when the height was N0 over 2, but it was going over both the positive and negative part of the bandwidth. Here we are only looking at the positive part of the bandwidth, and we are going to scale noise by N0. This is just a convention. Okay. In discrete time, your noise sequence is Nk or IID, and you take them as Gaussians with 0 mean and variance of N0 over 2. So you have noise which has a variance of N0 over 2 per dimension. And this was again shown by this theorem that when you project noise onto each of the orthonormal waveforms, you get the variance is N0 over 2. Okay. If instead of a baseband system, if we had a passband system, then instead of having a PAM modulator, we would have a QAM modulator. So if instead of PAM we had a QAM, then the main difference now would be that these symbols are going to be complex numbers instead of real. So what's the symbol interval now going to be?
1 over W.
It's going to be 1 over W. Instead of sending a real symbol, we are sending one complex symbol. So it's like occupying 2 dimensions. And our symbol rate is going to be 1 over W. Well, the energy per 2 dimensions is still given by ES equals 2 PT, or equivalently P over W. Okay? That's the noise samples Nk are still IID, but now they are complex Gaussians with 0 mean and variance N0. Or equivalently, they have a variance of N0 over 2 per dimension. So what we see here is that we can have analogous definitions for discrete time and continuous time. And one of the key parameters that comes up over and over again in the analysis is this notion of signal-to-noise ratio. The signal-to-noise ratio is defined as the energy of a per 2 dimensions over the noise variance per 2 dimensions. So that's the definition of signal-to-noise ratio. ES, well, it's 2PT or equivalently P over W. The noise variance is N per 2 dimensions is N0. So the definition is same as saying SNR equals P over N0 W. Okay. Are there any questions? The other notion we talked about last time is this idea of spectral efficiency. Okay, in continuous time, the definition is quite natural. It's denoted by symbol rho. The units are bits per second per hertz, and it's basically R over W. You have R bits per second over W hertz. So it's the amount of information bits that I'm able to send over the amount of bandwidth that I have in my system. In discrete time, we can also define the same idea of spectral efficiency, but it's usually a good way to think about a spectral efficiency from a point of view of a design of an encoder. What an encoder does is you have an encoder here. It takes a sequence of bits in. So say you have B bits coming in, and it produces N symbols. So this could be X1, X2, Xn, and you have a sequence of B bits, B1, B2, B subcapital B. This is how an encoder operates. It maps a sequence of bits to a sequence of symbols. Now, where does the encoder fit into this architecture? It fits right here at the front, right? You have bits coming in, you encode them, you produce a sequence of symbols, and you send them over the channel. So if I have this encoder, what's my spectral efficiency going to be? Well, you have to ask what the encoder does, right? So from here, we have a PAM modulator. Okay, so it's basically this. From here on, we are back to this system. So what's the spectral efficiency now for this system? Well, how many bits do you have per symbol? You have B over N bits per symbol. Now, how many symbols do you have per dimension if this is an orthonormal PAM system? You have one symbol per dimension, right? So you have B bits per N dimensions, in other words. Right. So in QAM, how many you have usually? How many symbols per dimension? You have symbols per dimension. Right. So in that case, the spectral efficiency, the units are bits per 2 dimensions, is 2B over N. You have B over N bits per dimension. Because the units are bits per 2 dimension, you get 2B over N bits per 2 dimension. Okay? Now, a natural question to ask is, how is this definition related to this definition here? This seemed quite a natural definition, and here we had imposed this encoder structure. Are the two definitions equivalent in any way? And in order to understand this, let us take a 1-second snapshot. So now in 1 second, I can send N equals 2W symbols. Because this is an orthonormal PAM system, I can send 2W symbols per second, or in 1 second I can send N equals 2W symbols. Because my rate is R bits per second, B equals R. In 1 second I can send R bits. So now my definition of rho, which I defined to be 2B over N, is same as 2R over 2W, which is R over W. So the definitions in continuous time and discrete time are equivalent. Okay? Now, why is spectral efficiency very important? Well, there is a very famous theorem by Shannon which gives us a nice upper bound on the spectral efficiency. Perhaps the most important theorem in communications is Shannon's theorem. It says that if you have an AWGN system with a certain SNR, then you can immediately bound the spectral efficiency by log to 1 plus SNR bits per 2 dimensions. This is a very powerful statement. Equivalently, the capacity of a AWGN channel is log to 1 plus SNR bits per second. So one important observation here is if I have a communication system and if what I care about is the spectral efficiency or the capacity, there are only two terms that are important. One is the signal to noise ratio, which is P over N naught W, which is defined here. So the individual units of P and N naught doesn't matter. It's only the ratio of P over N naught that matters. And the second parameter is the bandwidth W that we have in the system. So signal to noise ratio and bandwidth are in some sense fundamental to the system. An operational meaning of the encode of this theorem is that if I look at this encoder, then it gives me an upper bound on how many bits I can put for each symbol. The number of bits that I can put on each symbol is upper bounded by this term here, log to 1 plus SNR. I cannot put arbitrarily many bits per each symbol here. Now, in order to make such a statement, there has to be some criteria that we need to satisfy. And what is the criteria for Shannon's theorem? In order to make such a statement, I need to say that some objective function has to be satisfied. Because at some sense, I could just put any number of bits I could have on per symbol, right? The encoder can just put 100 or 200 bits. What's going to limit me? The probability of error. So this assumes that okay. Now you are not responsible for the proof of this theorem. It is in chapter 3 of the notes. Basically uses a random coding argument, which is quite standard in information theory. So if you already taken information theory or otherwise, you would probably have seen that the argument involves bounding atypical events that happen. So the probability of error is an atypical event, and we use asymptotic equipartition property to bound the error event. Now this is standard proof in Cover and Thomas, for example. Now the main difference that Professor Forney's approach is that he uses this theory of large deviations. Theory of large deviations basically gives you a bound on the occurrence of rare events, and it is like well known in statistical mechanics. So it's kind of a different approach to the same problem. The basic idea is same as you would find in a standard proof, but it comes up from this idea of large deviations theory. So for those of you who are taking information theory or already have seen it, I urge you to at some point take a look at this proof. It's quite cool. I already saw somebody reading this last Friday, and that was quite impressive. So I urge more of you to do that. So now that we have the spectral efficiency, a natural thing is to plot how the spectral efficiency looks like. So what I'm going to plot is as a function of SNR, the spectral efficiency. Typically, when you plot SNR on the x-axis, you almost always plot it on a dB scale. But I'm going to make one exception this time, and I'm going to plot this on a linear scale. So this point is 0 or minus infinity dB here. And I'm going to plot, well, I should call this actually rho Shannon, so that I don't confuse the notation. So we will define rho Shannon as log to 1 plus SNR. So this is rho Shannon here. And we want to plot rho Shannon as a function of SNR. Now, if my SNR is really small, log 1 plus SNR is approximately linear, so I get a linear increase here. If my SNR is large, then the logarithmic behavior kicks into this expression here. So now the spectral efficiency grows slower and slower with SNR. So this is the basic shape for my spectral efficiency. And this immediately suggests that there are two different operating regimes we have. One regime where the spectral efficiency increases linearly with SNR, another regime where the spectral efficiency increases logarithmically with SNR. So if SNR is very small, then we call this regime as power limited regime. And if SNR is large, we call this the bandwidth limited regime. Okay, so these are definitions. And let's see what motivates their names. Suppose I have a 3 dB increase in my SNR and I am in power limited regime. How does rho Shannon increase? A factor of 2, right? Basically, if I have a 3 dB increase in SNR, my SNR increases by a factor of 2. In this regime, rho Shannon increases linearly with SNR, so I have a factor of 2 increase in my spectral efficiency. What about this regime here? If SNR increases by a 3 dB, how does rho Shannon increase? It increases by 1 bit per 2 dimension. The units of rho are bits per 2 dimension. I have a logarithmic behavior kicking in. So rho is approximately log SNR. If I increase SNR by a factor of 2, I get an additional 1 bit per 2 dimensions gain. Okay? Well, if I increase my bandwidth in the power limited regime by a factor of 2, so this bandwidth here increases by a factor of 2, how does my capacity change? And if I'm in the power limited regime. There's no change, right? Or is there a change? I'm in the power limited regime here, and I increase my bandwidth by a factor of 2.
The ratio between P over N naught is the same if you get naught.
Right. What is my SNR? It's P over W N naught. So what happens if I fix P over N naught? Okay, yeah, so you had it. Basically, if I double my bandwidth, my SNR decreases by a factor of 2. So this term here is like SNR over 2. W increases by a factor of 2, and there is no change in bandwidth. So let's do it more slowly. So we are saying the, oops. And say my C is now W log 2 1 plus SNR. Instead of SNR, I will write P over N naught W. So this approximately is W times P over N naught W times log E to the base 2. And this is approximately, this is basically P over N naught times log E to the base 2. So in other words, in the power limited regime, changing bandwidth has no effect on the capacity. What happens in the bandwidth limited regime? Well, in this case, C equals W log 2, well, I can say approximately, and I can ignore this factor of 1 because P over N naught W is large, because my SNR is large in the bandwidth limited regime. I'm operating in this part of the graph. So this is P over N naught W. Now suppose I increase my bandwidth by a factor of 2, C prime will be 2W log 2 over P over 2W N naught. All right. This I can write it as 2W log 2 P over N naught W minus, this is to the base 2, so I can write a 1 here. And this term is approximately same. If I ignore the 1, if I assume P over N naught W is quite large, then I can just ignore the subtraction of 1. So I get 2W log 2 P over N naught W, or it's equivalently 2C. Okay, so in other words, in the bandwidth limited regime, if I increase my W by a factor of 2, the capacity approximately increases by a factor of 2. So that's what motivates the name bandwidth limited regime here. Are there any questions? Okay. Okay. All right. So it turns out that there are 2 points I wanted to say. First of all, one might ask that, fine, this seemed to be an interesting definition, that SNR is much smaller than 1 and SNR is much larger than 1. But is there any kind of hard division between the bandwidth limited regime and power limited regime? I mean, the general answer is no. It's basically because there is some point when the capacity behaves neither strictly logarithmically nor strictly linearly in terms of SNR. But from an engineering point of view, we take rho equals 2 bits per 2 dimension as a dividing point. Between the two regimes. And the one motivation to see why rho equals 2 bits per 2 dimension is a good choice is because this is the maximum spectral efficiency we can get from binary modulation. Okay? If you want to have spectral efficiency more than 2 bits per 2 dimensions, you have to go to multi-level modulation. And that's one of the reasons why this choice is often used in practice. The other point is that the bandwidth limited regime and power limited regime, they behave quite differently in almost all criteria that you can think about. So usually we do the analysis, we keep them separately and do the analysis differently in the bandwidth and power limited regime. And that's what we'll be doing in the subsequent part of this lecture and next lecture. So we'll start with the power limited regime. Now we already saw that in doubling the power doubles rho s, and doubling bandwidth does not change C. Okay. The other point I mentioned was binary modulation is sufficient in this regime because our spectral efficiency is less than 2 bits per 2 dimensions. So the idea is to have a strong code followed by binary modulation. What else? Right. Typically, the normalization is done in per information bit. What does this mean? When we are wanting to compare different systems, we will look at all the parameters normalized per information bit. For example, if we want to look at the probability of error, we will look at this quantity here, PB of E, which is the probability of error per information bit as a function of EBNO. This is an important trade-off that we wish to study in power limited regime. EB is the energy per bit. P sub B of E is the probability of error per information bit. Okay. So I want to spend some time on this EBNO because it's an important concept that we'll be using often in the course. So what is EBNO? It's sometimes also known as EB over N0. So it depends how you wish to call it. What is energy per bit in terms of ES? Well, ES over rho, right? Energy per bit, well, ES is energy per 2 dimensions, rho is bits per 2 dimensions. So EB is ES over rho. And you have N naught here. And ES over N naught is also our SNR. So this is SNR over rho. Okay, so that's how EBNO is defined. Now we know from Shannon that rho is always less than log 2 1 plus SNR, or equivalently 2 to the rho minus 1 is less than SNR. If I sub in here, this means that SNR is greater than 2 to the rho minus 1 over rho. And then we are just dividing by rho. So EBNO is always greater than 2 to the rho minus 1 over rho. And this is quite an interesting observation. For example, if you are analyzing the feasibility of a communication system, which has a certain spectral efficiency and a certain EBNO, then you can immediately check this relation to see if it is a reasonable system in the first place. What Shannon says is that EBNO is always going to be greater than 2 to the rho minus 1 over rho. So if you see that this relation is not satisfied, you immediately know something is wrong. This actually reminds me of an interesting anecdote that Professor Forney once mentioned when I was taking the class. I mean, he has been in this field since 60s, and so he has seen a lot of this stuff. He was saying when turbo codes, which is one of the first capaciting approaching codes in recent years, when they were proposed, they presented the results at ICC, the International Conference in Communications, and what they saw was that the performance was very close to the Shannon, to the limit that we can predict. So EBNO was very close to the ultimate limit. The EBNO achieved by turbo codes was very close to the ultimate limit that one can predict. They were at least 3 dB better than the best codes that were available there. So most people just thought that there was something wrong in the simulations, and they told them that there was a factor of 2 missing somewhere, so they should just double check. But it turned out when they went back and people actually implemented these codes, they were actually very close to the capacity. So it was quite, so sometimes you have to be careful. If the system, if you are not exceeding, if you are not going below this limit, it could be that the system is good. And when it is, it's a really important breakthrough. Okay. So one particular concept that comes here is the idea of ultimate Shannon limit. And basically, if we are talking about power limited regime, our SNR is very small. So our spectral efficiency is going to be quite small. Now notice that this function here is monotonically increasing in rho. It's easy to show that this function here increases monotonically in rho. You could just differentiate this, or the easier ways to do a Taylor expansion of 2 to the rho minus 1, the series expansion, and show each term is positive. So this term is always going to be greater than this term here. So I'm going from here to here. Limit rho tends to 0 of 2 to the rho minus 1 over rho. This is going to be a simple calculus exercise to show this is the natural log of 2, or in dB it's minus 1.59 dB. So no matter what system you design, your EBNO is always going to be greater than minus 1.59 dB. That's basically what this calculation shows. And when is it achieved? Well, it's only achieved when your spectral efficiency goes to 0. So if you have a deep space communication system where you have lots and lots of bandwidth and you do not care about spectral efficiency, then if your only criteria is to minimize EBNO, then you can design your system accordingly, check how much EBNO you require for a certain probability of error, and see how far you are from the ultimate Shannon limit. So in this way, in the power limited regime, you can quantify your gap to capacity, if you will, through this ultimate Shannon limit. Okay, are there any questions? Okay, so now let's look at the bandwidth limited regime. So we already saw two things in the bandwidth limited regime. If I double P, my spectral efficiency increases by 1 bit per 2 dimension. Similarly, if I double bandwidth, my C capacity approximately doubles. Now, because you want a spectral efficiency of more than 2 bits per 2 dimension, in these systems you typically do a multi-level modulation. So for those of you who are familiar, we do things like trellis-coded modulation and bit interleaved coded modulation and so on. If we have time, we will be seeing these things towards the very end of the course. This is not a subject of the course as such. The normalization in this regime is done per 2 dimensions. So if we want to normalize all the quantities we normalize them per 2 dimensions here. In particularly, we will be seeing probability of error as a function of this quantity called SNR norm. So this is the performance analysis that is done in bandwidth limited regimes. Here PS of E is the probability of error per 2 dimensions. What is SNR norm? It's defined to be SNR over 2 to the rho minus 1. Why do we divide by 2 to the rho minus 1? Well, that's the minimum SNR that you require for the best possible system. That's what Shannon says, right? So this quantity here is always going to be greater than 1 or 0 dB. So if you will, this is the ultimate Shannon limit in the bandwidth limited regime. If you have a system that is designed that operates at a certain SNR and a certain spectral efficiency, you can calculate SNR norm and see how far you are from 0 dB. If you're very close to 0 dB, then that's great. You have a very good system in practice. If not, then you have a room for improvement. And so in other words, SNR norm defines the gap to capacity. Okay. Okay, so let's do an example. Suppose we have an MPAM system. So we have an MPAM constellation. So how does it look like? Well, you have points here on a linear line. This point is, say, minus alpha, alpha, 3 alpha, minus 3 alpha, all the way up to m minus 1 alpha, and here minus of m minus 1 alpha. And assume m is an even number. So the distance between 2 points here is 2 alpha, any 2 points. Now we want to find the SNR norm given that we are using this constellation. So in other words, if I use this constellation in my communication system, how far am I operating from the ultimate Shannon limit? Okay, that's the question. So in order to find the, what we need to find is first energy per 2 dimensions. Does anybody remember the formula for MPAM? Well, there was a very nice way of doing it in 450. One natural way is to simply sum up all the coordinates here, square them, and divide by m. And because it's per 2 dimensions, we could do it. We have to multiply by a factor of 2 because it's per 2 dimensions, and summation of xj square. And if you work out, you will get some answer here. Another way that was shown in 450, which uniform quantization, exactly. So the idea here is you have a source, say, which is uniformly distributed between m alpha and minus m alpha. So you have a source uniformly distributed, then it can be easily seen by inspection that MPAM is the best quantizer for this particular source. Okay? So the Voronoi regions are just of equal width. Each Voronoi region is of width 2 alpha. So your mean square error, if you will, is 2 alpha square over 12. So it's alpha square over 3. Well, the variance in your source, which I will denote by sigma square s, is 2m alpha square over 12, or it's m square alpha square over 3. So your energy per symbol is the energy in your quantizer. So I'm denoting it by E of A in order to differentiate it by ES, because ES is 2 times EA. Okay? It's going to be m square minus 1 times alpha square over 3. So ES is 2 EA, and so we get it's 2 times alpha square m square minus 1 over 3. Okay, so can anybody tell me what the spectral efficiency will be for this system if I use an MPAM constellation? Well, how many bits per symbol do I have? Log 2m bits per symbol. So since it's bits per 2 dimensions, this one will be 2 log m to the base 2. Okay? So, well, now we have pretty much everything we need to find SNR norm. The SNR here is ES over N0. So it's 2 alpha square m square minus 1 over 3 n naught. But remember, n naught by definition is 2 sigma square, because sigma square is n naught over 2. That's the noise variance per dimension. So I have 3 times 2 times sigma square, or I will just write this as 6 times sigma square. And that's going to be, this is just multiplication, so I should not even write it. 6 sigma square. So this is alpha square m square minus 1 over 3 sigma square. Okay, so now SNR norm is SNR over 2 to the row minus 1. 2 to the row minus 1 is just m square minus 1. It cancels with this m square minus 1. And so I get alpha square over 3 sigma square. So that's the SNR norm if I use an MPAM system. Well, I plugged in for SNR 3 here, so I have 3 n naught, but n naught is 2 sigma square. Did I miss anything? Okay. Questions? Okay. So there are 2 important remarks from this example. The first remark is that SNR norm is independent of M. So I started with an MPAM constellation. So it's a different constellation for each value of M, right? If I look at my spectral efficiency row, it's different for each value of M because I can pack more and more bits per symbol as I increase M. If I look at my signal to noise ratio, it's also a function of m. But when I took SNR norm, remarkably the m square minus 1 term cancelled out in the numerator and denominator, and what I was left with is something independent of m. So this is actually quite an interesting result. What it says is, suppose I design a system, an MPAM system, that has this particular spectral efficiency, then my gap to capacity is given by this expression. Now if I use a different value of m, my gap to the ultimate Shannon limit is still given by this expression here. So by increasing value of m or decreasing the value of m, my gap to the Shannon limit is still going to be the same. For each value of m, I will have a different spectral efficiency, but I'm not getting any kind of coding gain, if you will, here. Okay? So this motivates that MPAM is an uncoded system. All of them have the same gap to the Shannon limit, regardless of what the value of m is. And so the second point to note is, if I look at the value of alpha square over 3 sigma square, I can make it quite small, right? I can even, if I decrease alpha really by a great amount, I can make this quantity smaller than 1. Okay? I told you here that SNR norm is always greater than 1. So what happened? Did I lie to you here, or did I do something wrong here? I mean, I can choose any alpha, right? And make this quantity as small as I please, and then I'm doing better than the Shannon limit. Right. So basically, what's missing in this calculation is probability of error. If I make alpha really small, what I have is all these points come closer and closer, and sure, seem like I'm doing very well at the encoder. But what happens at the decoder? There is noise in the system, and so I get too many errors. This lower bound clearly assumes that you can make your probability of error quite small, arbitrarily small, right? So in any reasonable system, I should also look at a probability of error. If I make alpha really small, I'm going to have too much error at the decoder, and so I won't be able to have a practical system. So the comment is SNR norm cannot be seen in isolation. We need to couple SNR norm with the corresponding probability of error. Yes? What I mean by uncoded system, that's a good question. What do I mean by uncoded system? All I'm really saying here is MPM system is a fairly simple system to implement, right? Now, irregardless of what value of m I get, I have a certain gap to the Shannon limit, which is independent of m. So if I start with this simple system, where I have bits coming in, each bit gets mapped to one symbol, and I send it over the channel, I have a fixed gap to the Shannon capacity. And this I will call an uncoded system. My only hope will be to improve upon this system. Okay? Any other questions?
So by the first point means you change m, but your alpha will not change.
Right. I'm assuming a fixed alpha. I mean, basically, you will see that alpha is a function of ES, right? And I want to right. So the question is, why do I want to keep alpha fixed? Right? Okay, so in order to understand that, I have to look at energy per 2 dimensions. If I normalize by m square minus 1, no, that doesn't work out.
It means there is some constraint on your energy per symbol, the ES.
Right.
Your constellation cannot expand enormously.
Right, so that I wanted to always thought by keeping alpha fixed. And I mean, the point is, typically you want to plot the probability of symbol error. Do I have that expression anywhere? Right there. PS of E as a function of SNR norm, right? And that will be, if I increase SNR norm, so it will be some kind of a graph, right? A trade-off. Basically, alpha will define the trade-off between SNR norm and PS of E. So as I sweep over larger and larger values of alpha for different values of M, then I will have a trade-off as a PS of E as a function of SNR norm. Does that make sense? So say I fixed a value of M, okay? I define SNR norm, which is alpha square over 3 sigma square. For this, I will get a certain probability of error now. So if I fix this value of SNR norm, I get a certain probability of error. What if I want to increase my SNR norm? The only way to do that will be to increase alpha. Does that make sense? Okay. Yeah.
Just a little counterintuitive thing. You're defining SNR norm as the gap to capacity, but it seems like, I mean, obviously as you increase alpha, as you increase your signal energy, you're going to do better and better, right?
Right.
Well, in terms of what? In terms of probability of error, like achievable probability of error? Or?
Right, exactly. So basically the point is, say I plot PS of E as a function of SNR norm or as a function of alpha square over 3 sigma square. So my curve will look like this.
But the gap to capacity is defined all the way over here on the left. Is that what?
Right, that's a very good question. You are going much ahead than what I thought. So basically at 0, say when SNR norm is 0, right? Well, this is in linear scale. So when I have 1, SNR norm is 1, I have the Shannon system. Basically, no matter for any SNR norm greater than 1, what Shannon says is your probability of error will be arbitrarily small, and here it will be large. So this here is the Shannon limit. And now in a practical system, what I want to do is I want to fix the probability of error. So say I like probability of error of 10 to the minus pi. So that's something that a system specifies. Then from that, I know the gap to the capacity. So if I require, this is my SNR norm, then this is going to be my gap. I wanted to cover it, but later. That's a good point.
So then it's not true then that the moment you're getting arbitrary, so you're getting
Right. This is a certain specific system, the MPAM system. What Shannon says that if you are anywhere here, you should be able to make a probability of error arbitrarily small. So your curve should basically look like something like this, if you will, or even steeper.
So what's the difference between that curve and the wider curve?
This curve and this curve?
Yeah.
This is basically what we achieve by an MPAM system. I don't want to go into too much of this because we'll be doing this, right? This is the next topic. Ideally, what we would want is something, basically, this is my Shannon limit. I want something such that the probability of error decreases right away as soon as I'm just away from the Shannon limit. Okay. All right.
Without coding, you don't really get to that.
Right, so that's a good point. So if I did not do coding, this is what I get. If I did coding, this is what I would get. So this is how much I can expect a gain from coding.
So in other words, basically this bound is basically if my channel, the SNR is such that, I mean, I'm so energy limited that my SNR is lower than, my SNR norm is lower than a certain amount, there's nothing I can do, basically.
Right.
That's what it's saying.
Because if you want a certain spectral efficiency, there's also a spectral efficiency, right? So, and if your SNR is much lower, you are out of luck.
So basically you have to make your spectral efficiency higher or lower.
Lower. Yeah, exactly. Okay. So now let us start with the probability of error analysis, and we'll start in power limited regime. So we have PB of E as a function of EBNO. We want to quantify this trade-off. Basically, what we are doing now is trying to quantify how these graphs will look like, at least for the uncoded systems today. We'll do coding next class, or 2 classes from now, as we get time. So say I have a constellation A. It's binary PAM. So it takes only 2 values, minus alpha and alpha. So I have these 2 points here, alpha and minus alpha. My receiveds y, symbol y is x plus n, where x belongs to A, and n is Gaussian zero mean variance sigma square, where sigma square is n naught over 2. And now what you want to do at the receiver is, given y, you want to decide whether x was alpha or minus alpha. That's a standard detection problem. So how will the probability of error look like? So suppose I transmit x equals alpha, my conditional density of y, let me make some room here, will be a bell-shaped curve because of the Gaussian noise. So this is P of y given x equals alpha. Similarly, if I had sent x equals minus alpha, what I get is something like this. This is P of y given x equals minus alpha. Excuse my handwriting there. And the decision region is at the midpoint, y equals 0. This is a standard binary detection problem. If y is positive, you will say x equals alpha was sent. If y is negative, you will say x equals minus alpha was sent. And your probability of error is simply the probability of error under this graph, under these 2 curves here. So we want to find what that probability of error is. Let me just do quickly the calculation in order to remind you. We'll be doing this over and over again. We'll just do it once. Without loss in generality, I can say this is probability of error given x equals minus alpha. Well, both the points are equally likely. So by symmetry, I can say that. So this is same as probability that y is greater than 0 given x is minus alpha. Now y is x plus n. So this is same as probability that n, capital N, is greater than alpha. Since n has 0 mean variance sigma square, this is a standard Q function of alpha over sigma. Okay, so that's the probability of error. Now there is 1 bit per symbol. For each x carries 1 bit. So probability of error is also same as probability of bit error. So this is also PB of E. So I have PB of E equals Q of alpha over sigma. And now I want to basically express it as a function of EBNO, right? So what is EB for this system? It's going to be alpha square. Sigma square is now n naught over 2. So alpha square over sigma square is 2EB over n naught. So now my probability of bit error is this Q function of root 2 EB over n naught. Okay, so let us plot this. So I'm on the x-axis, I'm plotting EBNO, which is in dB scale. On the y-axis, I'm going to plot the probability of bit error. Typically, what you do is you plot the y-axis on a semi-log scale. So this is 10 to the minus 6, 10 to the minus 5. If you want to do this in MATLAB, you can use this command semi-log y, and that does it. And so on. So can anybody say what will be a good candidate for this the x value at this point here? So what should be the EBNO at this point? It should be the Shannon limit, right? You cannot hope to go below than Shannon limit. So now what Shannon says is that, so I'm going to plot this as my Shannon limit here. This probability of error will basically is a standard waterfall curve. this is 2 PAM. And if you look at the x coordinates, then the value at 10 to the minus 5 is 9.6 dB. Okay. So if your system, as a system designer, if you care about probability of error at 10 to the negative 5, then your gap to capacity, or gap to the ultimate limit, if you will be this 9.6 minus of minus 1.59 dB. Okay, I should not erase this. Okay, so the first thing is at 10 to the minus 5, our gap to the ultimate limit is 9.6 plus 1.59 dB, and that's approximately 11.2 dB. Okay? Now, but there is one catch to this. This particular system has a spectral efficiency of 2 bits per 2 dimensions. Whereas if you want to achieve something close to the Shannon limit, you have to drive the spectral efficiency down to 0. So you might say that this is not a fair comparison. So if you do want to make a fair comparison, you want to fix rho to be 2 bits per 2 dimensions. So if you fix rho for 2 bits per 2 dimensions, you will get a limit somewhere, not at 1.59 dB, but at some other point. This is if you fix rho to 2 bits per 2 dimensions. Can anybody say what that point will be? Three over 2, 1.5. What will it be in the log scale? 1.76. Good. So what we do know, let me do the calculation here. If you fix rho to 2 bits per 2 dimension, your EBNO, we know, is greater than 2 to the rho minus 1 over rho, which is 3 over 2. And that is, if you remember your dB tables, 1.76 dB. Log of 3 is like 4.7. Log of 2 is like 3. So it's 1.76 dB. So in this case, your gap to the ultimate limit is going to be 9.6 minus 1.76, which turns out to be 7.8 dB. Okay? So now let us do the bandwidth limited regime. Now in bandwidth limited regime, the trade-off is PS of E as a function of SNR norm. Okay, so that's the trade-off we seek for. And the baseline system we will be using is an MPAM system. So now your constellation is going to be minus alpha, alpha, 3 alpha, minus 3 alpha, and so on, up to m minus 1 alpha. I always run out of room here. Minus m minus 1 alpha. So this is your constellation. Now what's the probability of error going to be for this constellation? Well, what's the probability of error for each intermediate point? There are two ways you can make an error. Say you send alpha. Your noise is either too small, so it takes you to minus alpha. Your noise is too high, so it takes you to 3 alpha. For each one, the probability will be q of alpha. This distance is 2 alpha, so it will be q of alpha over sigma, because we will be having your decision regions right here. So in other words, for each intermediate point, and there are m minus 2 of this, your probability of error will be 2 times q of alpha over sigma. Okay, and how many of them there are? There are m minus 2 of these, and if all the points are equally likely and you want to find the probability of error, you divide by m. For the two endpoints, the noise can only make an error in one direction. So you get 2 over m times q of alpha over sigma. You work this out, and you have 2 times m minus 1 over m times q of alpha over sigma. Now, we want to find probability of error for two symbols, because that's what PS of E is. Okay? So what's PS of E going to be? Well, it's in terms of PR of E, it's going to be 1 minus PR of E square. This is the probability you make error in none of the two symbols, and 1 minus that will be the probability of error you make in at least one symbol. And that's going to be equal to 2 PR of E, or it's 4 times m minus 1 over m q of alpha over sigma. Okay. Good, I did not write on this board. So now what remains to do is to relate alpha over sigma to SNR norm. And I had it on this board here. SNR norm we just did in the previous example for an MPAM system is alpha square over 3 sigma square. Okay? So I plug that in here. So I get PS of E is 4 times m minus 1 over m times q of root 3 SNR norm. And if m is large, this is approximately 4 times q of root 3 SNR norm. So we'll be plotting now probability of error as a function of SNR norm, similar to what we did in that part in the power limited regime there. So this is PS of E as a function of SNR norm. Now my Shannon limit will be at 0 dB. So this is my Shannon limit point. This is 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, and so on. This is going to be the performance of MPAM. And again at 10 to the minus 5, which will be the kind of performance criteria we'll be using throughout this course, we will see that this y-axis is 8.4 dB. So in this case, the gap to capacity is going to be 8.4 dB. So if I want a certain spectral efficiency and I use MPAM, I'm 8.4 dB away from the Shannon limit. The idea behind coding, as Aman pointed out, was to start from here and do coding to come closer and closer to bridge this gap. Okay? So are there any questions? We are almost in time. Okay, I think, yes?
Perfect code would just be literally like a step
Right.
all the way down.
That's what Shannon code is. Okay, I think this is a natural point to stop. We'll continue next class.